Okay, I guess we can get started today. And today we are going to talk about acidity and hardness. And so here are the things that we would like to talk. So first, I would like to introduce the one that is similar to alkalinity, which is acidity. And then I'm going to talk about how to report acidity and alkalinity, especially for the unit and some of the calculations. And then I'm going to talk about hardness, the definition and its significance. And then the source of hardness. And finally, we are going to talk about the units or some of the calculations of hardness. So first, on Tuesday, we have go through these plots, and yesterday we were trying to collect data to reconstruct these theoretical relations. And recall that we usually have three types of alkalinity: caustic alkalinity, phenolphthalein alkalinity, and total alkalinity. And for each of these alkalinity, we can say actually they are at different pHs. So at different pH, we know that there are different dominant species. So basically, we are trying to add the acid to make sure we have these species that are dominant. So basically, these alkalinities, which is a function of pH, these alkalinities, this should be Ca because this is caustic alkalinity. So we can say that they are the functions of the concentration of each component in the water. So if we assume we only have carbonate system in the water solution, and these alkalinities can be estimated or calculated by the concentration of these species. For more details about how do we derive these equations, I'm not going to talk about them here, but some of them are explained in the lab protocol. So in the first part of lab protocol, it describes some of like why we have these relations. But in general, this relations shows how much these chemicals can neutralize like the acid to reach these species as the endpoint. Yes.
Our experiment yesterday didn't have anything to do with caustic alkaline.
Right. So yesterday, because the sample is around 9, so we do not have the caustic alkalinity.
Okay. Does it appear on the graph?
Yes, it appears on this graph, but it doesn't appear on our graph.
Okay.
Yeah, because we start from the beta zone.
Right.
Yes. So similarly, for alkalinity, we add acid, and then the pH will drop. So it is shown like in this plot. But similarly, as we mentioned last time, we can add acid. So we can add base. So in this case, suppose our sample is relatively acidic, and then we add base. So basically, the volume will go this direction, and then the pH will increase. So we can imagine the curve will be something like this. So it is just the opposite of this curve. So the shape are the same, but the directions are opposite. And by adding the base, actually we can have the acidity. So recall that for alkalinity, the definition is that it is a measure of quantity of acid consumed to reach a certain endpoint. On the other hand, for acidity, it is the measure of quantity of base consumed to reach a certain endpoint. So basically, they are the same. But for alkalinity, we add acid, but for acidity, we add the base. So yeah, I would say they're kind of like this. So bioacidity is also important because it is related to the corrosion of the pipes. So it is similar to alkalinity. And as we mentioned before, in the water and in the pipe, the H plus the concentration of H plus determines the reaction direction of the corrosion. Like if we have more H plus, then we will have this more free electron. And when we have more free electron, the iron will be easily oxidized from 0 to 2 plus. And also, it also has some effect to humans. So basically, in the natural water, CO2 in a carbonated beverage is presented in excess of concentrations in natural water. And we know that for the soda, even though we have extra CO2s in the soda than natural water, but it is not harmful for us. But if we have water with mineral acidity, that is not good. So I will be talking about mineral acidity in the next slide. But for the mineral acidity, we have some other chemicals that is acidic that is in the natural water. And acidity is also related to the treatment of the wastewater because sometimes the wastewater may be very acidic. So we need to deal with that problem. And it is also related to acid rain. As we mentioned in the alkalinity, when acid rain drops to the ground, alkalinity is important because it can protect the pH change from the acid rain. But for the acid rain itself, we are interested about the acidity of the acid rain, like the rainwater itself. And the acid can come from the combustion of fossil fuels, especially when they have sulfur or nitrogen. And then the sulfur will become like the sulfuric acid, and nitrogen will become the nitric acid, and they can exist in the rainwater. In addition, for the acid rain, we know that when the water is in equilibrium with CO2 in the atmosphere, so what's the pH of that water solution? Do you guys recall the pH? What? Yes, it is about 5.5 or 5.6. But if we have some additional this strong acid in the natural water or in this rainwater, we can expect that the pH will be smaller than this value. So basically, acid rain is defined as the rainwater, like the pH of the rainwater, which is smaller than this value. And so do you guys have any questions? Yes.
The definition of caustic alkalinity.
Yes.
Is that third term H2CO3 or?
Yeah, this is CO. This is carbonate.
The like in the
This
formula,
one?
yeah.
Oh yeah, this is true because this is minus. So the existence of H2CO3 has the negative contribution because this is acid and it can provide 2H plus.
Okay, I see what's happening. Okay.
Yeah, and this one it can provide 1H plus. Similarly, this one only can provide 1H plus. So this is 1, but this is 2. Yes. So any more questions about this one? No. And the next one is about the sources of acidity in the natural water. And the main source of acidity in natural water is CO2. And because we know that the natural water is in equilibrium with the atmosphere. So we have some CO2 in the atmosphere, they can get into the water. And we have this equation C1, H2CO3. So it can provide H plus. But on the other hand, the CO2 can come from other sources. Like we know that we have some species or organisms living under the water or living in the water. And as they have the respiration, they will also release CO2. So the CO2 from these animals or organisms, they can also contribute to the acidity of the water. And we know they convert organic matter into CO2 and water. And another source is from a mineral, or we can say that it is a mineral acidity, and it can be present in the natural water because, for example, we have this. So this refers to the sulfides, and M refers to the like Na2 class metal ions. We know that in a rock, it's maybe something like that, but inside the rock, it is there is no oxygen. So we may have some sulfides inside the rock. And in this case, like when we are doing the mining, we will break down some of the rocks. So we have these sulfides in the rock. And when it is exposed to the atmosphere or in the air or in the environment, we have the air or oxygen, and we have the water. Under this condition, the sulfides will be oxidized into sulfuric acid. And in this case, we can generate H+. So we can contribute acidity to the natural water. And in some cases, we may also have some elemental like the pure sulfur. And when they are exposed to the environment with oxygen and water, they will also be oxidized into sulfuric acid, which makes the natural water become acidic. And so chemically, these reactions are relatively slow under normal temperature or the normal atmospheric pressure. But with existence of the microorganisms, they can accelerate this process. So in the environment, this process is not quite slow because of existence of microorganisms. On the other hand, the acidity can also come from the industrial waste or chemical waste. Like after we are doing experiments, we may just throw some of the, but we should avoid to directly dispose of our acidic solutions to the sink. We need to put that in the waste jar. Okay, so for this one, do you guys have any questions? No. The next one is about measuring of acidity. And here I just list the measuring of acidity and measuring of alkalinity together, so we can do some cross comparison. So basically, as mentioned before, the acidity is amount of, let me see. Oh, I guess this should be base. So acidity refers to the amount of base added to reach the point where some species are dominant. So in this case, for the mineral acidity, we can define it as this one. So for mineral acidity, we want to neutralize these two species. And finally, we can have H2CO3 and the existence of strong base. And for the mineral acidity, the equivalent point is 4.5, which is like similar to total alkalinity, like the pH, they're all pretty the same. And the reference chemicals, species, they're also the same. And for CO2 acidity, we are going to neutralize this one only, and the endpoint is around 8.3. And in this case, we can see that the dominant species will be H bicarbonate. And we can see this is pretty similar to phenolphthalein alkalinity. On the other hand, we have total acidity, which we just neutralize the strong base, and the endpoint is around 11. So this one is pretty similar to caustic alkalinity. And under this condition, the dominant species is H2CO3. So for this one, do you guys have any questions? No? And similarly, we have different species to express its volume, to express its value. And here are some more explanations about acidity. So for mineral acidity, as mentioned, that is amounts of H, like the base required to reach this equivalent points. And in the lab, we usually use this methanol orange to measure its, to quantify its pH. So basically, at acidic condition, the color is red, but in the basic condition, the color is orange. So basically, we use this one as an indicator for the titration, but we are not going to do these experiments in this class. But here I just want to show the indicator. And for the CO2 acidity, and the endpoint is pretty the same as alkalinity. So we still use the phenolphthalein and to present, to use the phenolphthalein as the indicator. And for the total acidity, I think this is not very rare, and I didn't find the indicator that we use. But anyway, we can use the pH meter to measure its pH. And that's it. Oh, so for this one, do you guys have any questions? No. The next one is about the units of alkalinity, because we are going to report alkalinity. So the units of alkalinity was described in the lab protocol. So this is the third page. And in the lab protocol, it also demonstrates how to calculate alkalinity based on the data that we have. And here it shows the equation. Note that we have some of the assumptions, but I want focusing on this equation. So from this equation, we can see that the unit of alkalinity is milligram calcium carbonate per liter. So basically, when we are reporting alkalinity, we just convert everything to calcium carbonate in milligram per liter. I think the reason is that in industry, calcium carbonate is very common, so they use this one to as a unit. And this can be calculated by A times N times this 5,000, 50,000 divided by the volume of our sample. And here A is a total volume in milligram of the standard acids that we used, like HCl. And N here is a normality of the standard acids we used. And in this case, in HCl, the normality is 1 because it provides 1 H plus. And this 50,000 is a conversion factor. So we can just remember this. And in the lab reports or in the homework assignments, we may use this table to integrate the alkalinity value. So you guys may take a look at the whole part before you start doing the assignment. So any questions about this one? No. Yeah. And the next topic is about hardness. So the hardness is defined as the sum of all polyvalent cations. So basically, the hardness can be expressed as the concentration of calcium, magnesium, iron, magnesium, and blah, blah, blah. But note that they should be polyvalent cations. In other words, the concentration of sodium, potassium, this guy does not count. But in natural water, the main components are calcium and magnesium. And the iron and some other species, the concentrations are usually pretty small. So for many of the situations, they may be very small, so we may ignore them. So the simple definition of water hardness is the amount of dissolved calcium and magnesium in the water. So the total hardness can be expressed as this one. So And the total hardness can also be divided into two parts. The first part is permanent hardness. The next one is temporal hardness. The difference is that for the temporal hardness, it is caused by the presence of dissolved bicarbonate minerals, especially like the calcium bicarbonate or magnesium bicarbonate, and they can be removed by boiling. And here shows the equation. We can see that we have this calcium bicarbonate, and that is dissolved. That is dissolved in the water. And under the heat, if we have the heat here, then it will be decomposed into calcium carbonate, which is a precipitation, and H2O and CO2. And we also know that under very hot temperature, the CO2, it is a gas, then it will escape. When it escapes, the concentration of CO2 in the system will decrease, which help us to make this equation going forward. So under hot conditions, this equation go to this direction is very favorable. And similarly, we have this magnesium bicarbonate, and it is under the same process. So when we are boiling the water, after using many of the times, we can see there are some white stuffs on the surface of the pots or the pipes. And for the permanent hardness of water is a hardness that cannot be removed by boiling. For example, we have this calcium chloride in the water. It contributes to the hardness, but we cannot remove it by boiling the water. And so for this one, do you guys have any questions? No? Okay. Then for the water hardness, we have different classifications. Like we have soft water, hard water, very hard water, and we have something in between. And on the right side, I just collected some of the classification standards from the web, from the internet, and we can see for this one, like it has, so for the units of hardness, it usually as same as alkalinity. It has a milligram of calcium carbonate per liter. So the units is usually like this. So we can say from this one, we have different ranges, and according to different ranges, we have different classifications. And this is another one. Again, we have different amount of calcium carbonate. And in this one, it also has another types of classifications. And the point here, I want to show that based on different source or different literature, the classification may be different based on the value of the hardness. So when we are reporting the results, it would be better to report the value first, and then we may mention its classification, and then we cite or we reference the source of this standards. So this will be the most accurate way to report the water hardness. And here I have a question for you guys. So what is the hardness of milk? Because we know that milk contains lots of calciums. So do you guys think, like let's say this one, do you guys think what's the classification of milk? If you guys have any ideas? What? Excuse me? It is very hard.
I would say moderate, but I don't know.
Moderate, yes. So first, what's the calcium content in a regular milk? Do you guys have any ideas? No, I did some research, and let me see if I can pull that out. Keep. Yes. So from Google, it says it contains 100 to 1200. So the milk contains lots of calcium in the milk, which is making sense. And so for the hardness, we need to convert this calcium into calcium carbonate. So basically we can use this one divided by 14 times 100, and the result is 3000 milligram per liter. We can say this is very hard. But usually we do not consider the milk as hard water. Okay, anyway, so for this one, do you guys have any questions? Yes.
Why don't you divide by the 40 real quick?
Because
Why don't you divide by the 40?
40, oh, because the molecular weight of calcium is 40, and the molecular weight of calcium carbonate is 100. So any more questions? No. Here shows the water hardness in the United States on the right side. And to comparison, I just grabbed the geographical map of United States on the left side. And if we are, by looking at these two maps together, I guess we can find some clue. So in this, in the map on the right side, we can see the red one refers to higher hardness and followed by the white one. And we can see most of the water that has very strong hardness is around here. And if we are going back to this map, we can see that is around some mountainous areas. So I'm not the expert of this, but I would probably say the water hardness is kind of correlated with this geographical characteristics. But in Maryland, I guess we are around here, and the water hardness is relatively low. So we are caring about water hardness in the natural water. Why? Because it is related to our health. So the influence of water hardness to our health, actually, based on what I know, it is a little bit controversial. And I did some research on the papers, and I find this one. So this one discusses the potential health impact of hard water. And this is a reviewed paper published in like about 10 years ago. And let's just take a look at its abstract. So let me just, okay. So that we can just say, has been accumulated by environmental factor which appears to be influenced mortality, and in particular cardiovascular mortality, and this is the hardness of the drinking water. So we can see that drinking water may have some other adverse effects to our health. And in addition, several epidemiological investigations have demonstrated the relation between risk of cardiovascular disease, growth retardation, reproduction failure, and other health problems, and the hardness of drinking water, or its content of magnesium and calcium. So we know that the existence of these two cation ions has some relation to our health in the drinking water. And in addition, the acidity of water also influence like the reabsorption of calcium and magnesium in the renal tubule and something like that. So basically we can see that except for hardness, the acidity has also some health effect to the humans. So if you guys are interested, you can find this paper and read it. So, but based on what I know, like some people say the hardness will not influence our health, but some people say it will influence. So I think it is also like we have no common agreements on this one. Okay, so next one is about aesthetic effects. So basically, for the soft water, it is good for washing our clothes, but for the hard water, because it has the calcium and magnesium in the water, they will react with the salt. Finally, we will form the precipitation, which is insoluble. And so I just find the example of using the hard water to wash this clothes, and the color becomes to this very light yellow. But actually, if I only tell you this is my new clothes, I think no one will suspect that. And so nowadays, we usually do not use soap, but we use some like detergent, which can also form the soluble material when we are doing the washing. So that would be better. It will also influence it also have some economical significance. For example, like for the soft water, they are more economical for cleaning clothes because the hard water will consume some of the detergents or the soaps, which is bad. On the other hand, it may also have the problem of scaling. As we mentioned before, like we have some hard pipes here that is used to heating the water. And if the water have some hardness, and we will have some precipitations on the surface of this pipe. And we know that these stuffs are calcium carbonate and magnesium carbonate on the surface. And because of the coating of these minerals on the surface of this pipe, then the heat cannot transfer from the pipe to the water, which will cause some problem. And here I just found a picture showing like if we are mixing the hard water and soft water with the soap. For the soft water, we have so many bubbles, but for the hard water, it will be very untransparent. Here I would like to talk about the source of hardness. And so the main source of hardness comes from chemical or biological weathering. So in the upper layers of the soil, because we have air and the carbonaceous materials or the bacteria, so we have the CO2. The CO2 can come from the atmosphere, and they can also come from the respiration of the organisms. And when this CO2 is in equilibrium with the water in the soil, because in the soil, sometimes we may have some water in the soil. And in this soil water, the CO2 will dissolve in the water. And in the particle in the soil particle, we have this calcium carbonate. And with large amount of CO2 from the environment, we can see that the reaction will go to this side. And in this case, the calcium carbonate will be dissolved into calcium bicarbonate. And then when the rain just goes deeper, we can see that the rainwater with a lot of calcium bicarbonate, they will get into the underground water and then get into the watershed. And so this is the main source. On the other hand, we may also have some iron or manganese in the water. And so in this case, carbonic acid is not quite strong, so they may not be able to dissolve iron or manganese in the water. But on the other hand, with the existence of bacteria, they may convert this one to here. So basically, in here we have the iron in the which has 3 charges, and this one we have manganese with 4 charges. And so basically, the metals that has higher charges, they are easier to precipitate because they have strong attraction to the negative charged ions. But when they have 2 charges, they are relatively more soluble. So in this case, some of the bacteria or microorganisms, they can convert the 3 plus to 2 plus, or they can reduce this 4 plus to 2 plus, which makes them a little bit more dissolvable, and they will be dissolved in the natural water and then go to the watershed. And they may contribute some of the hardness of the natural water. And so for this one, do you guys have any questions? No? And then when we are reporting the hardness, we are going to use some units, and it may also involve some of the calculations. As we mentioned, we use the milligram per liter as calcium carbonate as the units of hardness. But sometimes we may also use this milli equivalent per liter or equivalent per liter to express the hardness. So let's look at this one first. In this case, we use CQ to express the this equivalent per liter, and it can be calculated by the concentration by C over EW. In this equation, C refers to the concentration of the chemical in gram per liter, and EW refers to the equivalent weight in gram per equivalent. So the C is usually known because we know the concentration of the chemical, but for EW, it can be calculated by this equation. So EW equals to MW, which refers to the molecular weight, which is usually known. And N here refers to the ionic charge or valence in equivalent per mole. So I think this is the most important one. So for N, it may be 1, 2, 3, or other values. And for calcium carbonate, N equals to 2, because calcium carbonate can provide like a calcium, and the calcium has 2 charges. So for calcium carbonate, N equals to 2. And here is just a quick example. So for calcium carbonate, we know that N equals to 2, and the molecular weight of calcium carbonate is 100. So the equivalent weight of calcium carbonate is 50 because N equals to 2. On the other hand, if we have 100 milligram calcium carbonate, it means that we have 0.1 mole per liter of calcium carbonate in a solution, but we have 0.2 equivalent per liter of calcium carbonate. Or we can understand it as calcium carbonate can combine 2 H plus in the water. Yes.
Yeah, so I just want to clarify. So like N is basically just the charge of the cation.
Yes.
So like if it was like potassium carbonate, I don't know if that's N, but like then the N would just be equal to like 1 plus.
You mean this one?
Yeah.
So this is a good question. How do you guys think? Because the calcium only has 1 charge, and it does not count as hardness. Right? Yeah, so we don't care about this one or the sodium, but we may care about Fe2 plus because it has 2 charges. We may also care about 3 plus. So in this case, I will show an example later so we can know how to calculate when it is not equal to 2. And by knowing this equivalent concentration, we can use this CQ to calculate the hardness as calcium carbonate. So we just use this C equivalent concentration times the EW of calcium carbonate, so which is 50. We can remember this number, and then we can get this result. And I guess this is a little bit confusing. So let's look at an example.
What is that blue? Sorry.
Which one?
What does the H stand for?
H. Oh, H refers to hardness.
Oh, okay.
I just use H, but you can use either symbols.
Okay.
And here is an example. So suppose we have a sample of groundwater that has calcium, magnesium, like iron, which we have 3 charges, and we have sodium. And in this case, we have the question, what is the total hardness in the units of milligram per liter of calcium carbonate? So basically, when we are talking about hardness, we do not care about the cation ions. We are not caring about the, so cation ions refers to, it has positive charge, right? And the anion refers to the negative charge. So we are not caring about the anions. We only care about the cation ions, that's the ions that has positive charge. So in this case, first we know that the equivalent weight of calcium carbonate, we can remember it, which is 50. So we can have this first. And then we just need to calculate each species one by one. So for calcium itself, the molecular weight of calcium is 40. So because it has 2 charges, so the equivalent is 20 because n equals to 2. And then we can use this to calculate CQ, which we use the concentration of calcium divided by the equivalent of calcium, and we can get this CQ. And to calculate the hardness of calcium, it equals to the CQ times this equivalent weight of calcium carbonate. This equals to 50, and this CQ we have already calculated. So we just plug the number in this equation, we can get the hardness. The hardness contributed by calcium, which equals to this one. And similarly, for magnesium, it also has 2 charges. The only difference is that the atomic weight or the elemental weight of magnesium is 24. So we just use different value, and then we can get the hardness that is contributed by magnesium, which is this value. And for this iron, because it has 3 charges, and so in this case, the n here equals to 3. So we can calculate the equivalent weights of this Fe3 plus. And for Fe3 plus, it only has 1 milligram. So we just use 1 divided by this equivalent weight. And we can get the CQ of Fe3 plus. And we just do the same thing. We use this CQ times the equivalent weight of calcium carbonate. And then we can get the hardness contributed by iron. And still, we can also calculate sodium. The sodium n equals to 1. And then we can do the same thing, calculate CQ and calculate the hardness contributed to sodium, which is this one. So the question is, what is the total hardness? So when we just add them together and then get the total hardness. And here I just have a question, and I think we have already discussed this. So is the total hardness equals to this one or equals to this one? If this is an like multiple choice question, which one do you guys choose? Suppose this is A, this is B. How many of you guys think it is A? How many of you guys think it is B? So what's the difference? The B is the sum of all of them. A is the sum of all of them except for sodium. And because sodium only has 1 charge, so it does not count in hardness. So we should not add this one. That is why we should choose this one. So yes.
I remember like a couple of slides ago, I forgot what it was, but it showed the total hardness is like the sum of all of them, but it didn't count iron.
Let me.
And I forgot the charge of iron in it.
Cheap. Like the definition of hardness, right?
Like I think it's equal to concentration of
Yeah,
calcium
that's the one.
plus.
Yeah.
Yes.
So even the positive 3 charge is, you have a 0, so would we not count
Oh,
higher?
oh, sorry. So for this one, because the concentration of this species, they are relatively small in the natural water. So sometimes they can ignore this. Because they can ignore this, I just use 0 to note this.
But if it was a problem, we would factor in there.
Excuse me?
If it wasn't like a problem that like you just gave us, we would factor in.
Yes, you can. You need to add that.
Okay.
But from this example, we can also see that the concentration of iron is pretty small. And we can see the contribution of the iron compared with magnesium and calcium, it is also negligible. But in the calculation, in the test, in the quiz, you guys need to consider this one. Yes.
So question. If this is like a quiz or something, do we even have to go through the calculation of what's that again? The last one. We have to go through the calculation of Na plus.
Of what?
Of Na plus.
No, because it is not counted as hardness.
So we don't have to like show the work.
No.
Okay.
Yeah. But so in practice or in the homework or in the quiz, I will give you anything that we can detect. So you guys need to determine, shall we include this or not? Shall we include this or not? Okay. So any more questions? No? Okay. And here a summary. But at the end, I would like to talk a little bit more about the quizzes that we have done. And so for the first one, this is a common mistake. So where can you find the details of course-related policies? I think like many of you guys choose this one. I'm not sure, but I think I only post this on the syllabus. I didn't post this on the ELM's homepage. So, but if you guys can find it, just let me know. And for question 11, so even though you got the wrong answer, I will give you credit. So you can check if I didn't give you this credit, just let me know. I think this is a little bit confusing because at the beginning of the class, I mentioned that they may have the form like this. So some of the students can attend the Zoom, but I didn't well define this situation. Is this a live or this in person? So I think that this is my bad. So I will give you this credit. But here I would like also to clarify that. So for this one, if you guys on Zoom, it is okay to not open your camera. But in the future, when we have some real online class, and at that time, you guys should open your camera. And I will let you guys know when we get to that situation. For quiz 2, we have we may also have something like this. So some of you guys may choose the wrong answer. So basically, we are going to convert the molarity into normality. And as I mentioned in lecture 2, when we are doing the conversion, we need to consider the situation, especially for the chemical reaction. We can see that both of them are bicarbonate, react with water, but they are doing the reaction under different conditions. So we have different results. In this case, we only generate one OH minus, or in other words, the bicarbonates only attacks or only grab one H plus. So only one H plus is involved in this chemical reaction. So the number should be 1. But in this case, the bicarbonate, it grabs 2 H plus and it generates 2 OH minus. So in this case, it should be 2. And for this one, because the calcium has 2 charges, so they choose 2. And similarly for this one, it dissociates with 1 H plus. So only 1 H plus is involved in this reaction. So it is 1. And for this question, I think some of you have some problems with the pKa of HOCl. So as I mentioned, when it reaches to pKa equals to the pH plus like log 10, the concentration of the acid divided by the concentration of its conjugate base. And we know that when this one equals to 0, in other words, the concentration of the acid equals to the concentration of its conjugate base, pKa equals to the pH. So we want to find the point where we have 50% of this acid. So if we all the way go to here, and then we can find it is this one. So the pH should be, like the pKa should be around 7.5, something like that. And for this one, this is also common mistake. I think this could be like you guys misinterpret the unit. So in this case, this unit is gram per cubic meter, centimeter, and the question is gram per cubic meter. So the correct answer should be this one. And I guess because like if we have gram per centimeter per cubic centimeter, that should be correct. And the last one is about the distribution of ammonium, and this is Kb, which is similar to Ka, but I didn't talk about. So this is base association constant. So this is similar to Ka. So at this pH equals to Kb, which is 4.60. So in this case, we can still get the plot, something like that. And under basic condition, we have this NH3 or NH3OH, and this is NH4 plus. So the question is in the natural water. In the natural water, it is around 7. So the main species should be this one. And that's it for this class. So I think Maria has sent the link for the collaboration. So you guys need to upload your Alkalinity and Hardness lab data into the collaboration. And again, I would like you guys to read the lab protocol, especially for the part 1 for the theory, which will be helpful. And also, Laura is grading assignment 2. So if you guys have any questions about assignment 2, I would recommend you guys to ask Laura, because when she gives you the feedback, because she will grade that is guaranteed. Also, Maria is grading assignment 3. So if you guys have questions, you may email to Maria. So we have different TAs responsible for different assignments.
Uploading that data, do you want us to put in like a spreadsheet and then upload it? Because right now it's like one. Like how do you want us to upload it?
I'm not sure what she's, but it will be better to upload in the data sheet.
Okay.
Yes.
Because right now the collaborations, I think that's like a
Google
Microsoft
file.
yeah.
And you kind of have to like, it's not easy to just input your data in there right now.
You mean in the Google? Oh, yeah, that's a good. I will discuss with Maria to see if we can create a Google Sheet instead of Google Doc.
Okay. Yeah. Then like each group has like a tab and we can enter our data in it.
Yeah, yeah, I will see this. Okay. Okay, thank you.